Hi everyone, we're back. We are going to put the finishing touches on chapter 4. One of the things that we need to tidy up the end of this chapter with is determining rho. And basically what that is in 4.1 we learned how to determine the R value. The R value, or the correlation coefficient, tells us the strength of the linear correlation for a sample. But the question is that strength strong enough that we can say, yes, there still is a correlation in the entire population, not just the sample that we're working with? To do that, we're going to learn how to test rho, and you will need table 4.4 at the top of page 134 in your textbook. We're going to continue with the caribou and wolf population problem that we have been working on, and we're going to use our calculator and our determined R value and the table on the top of page 134 to test rho. We'll be right back. Okay, what exactly is rho? Well, in 4.1 we learned to calculate the R value, or the sample correlation coefficient. And that gave us the strength of the correlation, right? Was it moderately strong? Was it moderately correlated? Was it a strong correlation? But that only gave us the strength of the correlation for the sample data. Rho is the exact same thing, but instead of being for the sample, it's for the entire population. Now, it's unreasonable to imagine that you gather all of the data and run the calculations for the entire population. So what we do is we take the R value and we take a designated measure. If you look on page 134 from your text, we take either the measure of 0.05, let's zoom in here just a little bit, we take either 0.05 or we take 0.01, depending on what's the risk that we're willing to take that we might be wrong. So obviously, the smaller the value we take, if alpha is 0.01, the stricter the calculations are, and therefore we can be more certain that there is a correlation in the population like we found in the sample. So it's fairly easy to use once we know what alpha we're going to take. All we do is we take our absolute value of the R. The absolute value of the R value. So let's go back to our caribou population and wolf population that we've been working with for the last few videos. And I am going to enter this data into the calculator. So first thing I need to do is to clear my lists. Then I will go again to edit the lists and enter my data value: 30, 34, 27, 25, 17, 23, 20. And again in list 2, 66, 79, 70, 60, 48, 55, and 60. I'm going to quit, go to statistics, calculate my linear regression in statistics form, a plus bx. My x's are in list 1, y's are in list 2. If I want, I can go ahead and store that in the y sub 1, and I'm going to calculate. Now I have an r value of 0.915, which is what we needed. So we're going to take of our caribou versus wolf population. The R value is approximately 0.915. So to test rho, we take the absolute value of R, which in this case, since R is positive, it's still 0.915. And we take our alpha. If our alpha is 0.05, that means we're willing to take a little bit of risk here. It's not a life or death situation. We're just determining the wolf population based on the number of caribou and Denali. So we find the table entry row headed by n, right? How many n data pairs do we have? If you recall, back on the problem, we had 7 data pairs, so I'm going to go down to n for 7 data pairs, and I take the absolute value of my r value, which was 0.915, and since my r value of 0.915 is greater than or equal to 0.75, then I can conclude that there is some correlation in the entire population. I can go ahead and conclude or decide that yes, there is correlation in the entire population. I can't say how strong it is, but I can say, that there is some there. If the R value was not 0.75 or greater, if it was less than that, then we could say that our R is not significant. We don't have enough evidence to decide that there is any correlation between the wolf and the caribou population. But in this case, if you look, even if we were stricter with our alpha value, even if we tested all the way down to a population of 0.01, our R value of 0.915 is still greater than that 0.87. So we can be fairly certain that yes, there is correlation in the entire population of caribou and wolf based on the R value. So in conclusion, or to summarize what we're talking about today, Rho is simply the population correlation coefficient. It's the same thing as R, but instead of being just for a sample, it's can we go ahead and conclude that what we have done in our sample will also hold true in the entire population. And when we do that, we test at different strengths, right? We test at either 0.05, which means we're not going to be as strict with the data. We can go ahead and make some error here and it won't significantly affect what's going on. Or we're going to test very strictly all the way down to 100th. And in this case, we're much stricter with our conclusions. So you take the absolute value of R and you find the correct column in the table. N is the number of data sets you have, and you find the number of data sets depending on how strict you're going to be with your population, and you can determine from there if you have correlation in your entire population. So what we're going to do to try this out is, if you would, go ahead and look at problem 20 to try it out on your homework tonight. This is problem 20 on page 34. Problem 20 on page 34. We're going to use table 4.4 at the top of the page and explore the significance of R based on different sample sizes. So you're going to look back at problem 19. But it's not going to take a lot of work this time because you know how to find R value using your calculator. It will simply be a few button pushes, a few calculations to determine if you have enough significance based on the different sample sizes. And we'll discuss the answer to problem 20 when you get back to class tomorrow.